Hello everybody, welcome to your lecture for Skill Check. Today we're going to work through an example where we conduct a two-sample t-test. And so the skills that we're going to be looking at will be knowing how to determine the critical value for the test, computing the test statistic and the p-value of the test, and using that p-value to assess the strength of the evidence against the null hypothesis. So here is the scenario. We're imagining that there is a company that makes light bulbs in a plant located in Dartmouth, Nova Scotia. So Juliana, the plant manager, takes a random sample of 60 bulbs every month and measures the time before each one burns out. So this would be a method of quality control for the product. The question then, Juliana wants to see if the mean lifetime for the population of bulbs manufactured in June is the same as it was for July. This is the question that she aims to answer using statistical techniques. And so we look at some data. In June of 2023, the sample mean lifetime was 5,224 hours with a standard deviation of 172 hours. In July, the sample mean was a little bit less. It was 5,017 hours with a standard deviation of 188 hours. Now, so from this data, it is possible to calculate the approximate degrees of freedom for the difference between sample means. So using software, Juliana found that degrees of freedom to be 117. Now here I just want to emphasize that for this kind of problem, for a two-sample t-test, you will not be expected to know how to determine the degrees of freedom. It is a bit of a calculation. We're not going to expect you to do that. We're just going to tell you what the degrees of freedom is. And so in this case, the degrees of freedom, 117. Right, so the first question, what are the null and alternative hypotheses in this scenario? Well, Juliana wants to see if the mean lifetime for the population of bulbs manufactured in June is the same as it was for July. So this is the comparison we're going to make. We can let mu1 represent the mean lifetime for June, mu2 represent the mean lifetime for July, and so the null hypothesis is simply that those two mean values are equal to each other, which is to say that their difference is 0. In other words, there's no difference. So that's the null hypothesis, and keep in mind that when we conduct our hypothesis test, we're assuming that this null hypothesis is true. The alternative in this case is two-tailed. We're looking to see whether there's evidence that the mean value has actually changed from June to July. And so if we ask, has the value changed? That's like saying, are the two values different than each other? And so we have, in this case, a two-tailed test. Second question. Juliana will conduct the test at the 5% level of significance. And so we need to find the critical value for her test. And also we want to ask ourselves, what is the probability that Juliana will make a type 1 error, or in other words, a false positive? So let's go to a picture. Here we have a picture that represents our test statistic under the assumption that the null hypothesis is true. And in this case, it's a t-statistic because we're going to be using a standard error for the difference between sample means. And that t-statistic has 117 degrees of freedom. Now we have to go, of course, to a z-table to determine the critical value for the test. And in this instance, we're looking at a two-tailed probability because it is a two-tailed test. We were asked to conduct the test at the 5% level of significance. So we want to put 5% in those two tails combined. And the degrees of freedom that we need to use is 100. So the true degrees of freedom, again, is 117. And we need to select from the table a value that is as close to 117 as possible without being larger than 117. And so that has to be the 100. And so looking at the table, we can see that our critical value is 1.984. So the picture then is we put plus or minus that critical value. Those critical values place 2.5% into each tail and 95% in the middle. So that makes it a 5% test. Our decision rule then is that we will reject the null hypothesis at the 5% level of significance if our test statistic in absolute value is greater than that critical value. So that's just a fancy way of saying we will reject the null hypothesis if our test statistic either falls in this lower tail or in this upper tail. Now, part of the question was to answer what is the probability of making a type 1 error. In this case, the probability of making a type 1 error is 5%. In other words, it's the same as the level of significance for the test. Now, I just want to make sure we all understand why that is. So again, it's important to remember that whenever you conduct a hypothesis test, you're starting with the assumption that the null hypothesis is true. And so this distribution, this t-distribution, is the distribution of the test statistic assuming the null hypothesis is true. So what that means is, even if the null is true, there's still a 2.5% chance that our test statistic is going to fall in this lower tail. And likewise, there is a 2.5% chance that our test statistic will fall in this upper tail. And so in total, there's a 5% chance that we will wind up rejecting our null hypothesis, even though it is true. Next question. So let's suppose Juliana decided that a 5% chance of a false positive is too high. So let's reduce the level of significance to 1%. Now what is the critical value for the test? So again, we go to the t-table. This time we're looking at a two-tail probability of 1%. Again, it's 100 degrees of freedom as our approximation. And now we get a much larger value, much larger than before. We get 2.626 as the critical value. And so plus and minus 2.626, those are the boundaries that will put 0.5% into each tail of the distribution and 99% in the middle. And so here now our decision rule is we will reject the null hypothesis at the 1% level of significance if the absolute value of our test statistic is greater than this critical value. I can see, looks like I have the wrong number there. Let me just go back for a second and check. 2.626, okay. So I'm going to have to fix that. Let's go here. This should have said 2.626. Great. Okay. Next question. Now we're going to use the data to compute the test statistic, and we're going to draw a conclusion from the result. So here's the data. In June, we have a sample size of 60. We have a sample mean and a sample standard deviation. In July, again, same sample size. We have a sample mean and a sample standard deviation. We need to plug these values into the appropriate formula to get our test statistic. And so as we learned in class, the test statistic in this case, well, keep in mind here, our random variable is the difference between those two sample means. So this is our random variable. This random variable has a standard error of what you see on the bottom of this fraction. That's the standard error of this random variable. Under the null hypothesis, this random variable is centered at mu1 minus mu2, which is 0. And so, plugging in some numbers, we put 0 in place of the difference between the population means, again, because we're assuming the null is true. And then for the rest, we just put in the numbers that we have. So here's the mean for June, the mean for July. Down here we have the standard deviations for those 2 months, and we're also accounting for the sample size. Now, this calculation can be a little bit tricky if you're not particularly confident in the use of your calculator. So I'm just going to go through that. And in particular, I want to show you how you can use the memory function on your calculator to make this a bit easier. So of course, your calculator isn't the same as what I have here, but almost certainly the one you're using has some kind of memory function. And so M plus is the button you will press to add some value to the memory. So let me show you what I mean. So I'm going to calculate this, this standard error first. So I'm going to go 172. I'll square that, divide by 60, equals. And so this number is this first fraction. I'm going to add that to my memory by pressing this button here. So check it out. See that number? If I erase and I press memory recall, the memory recall will give me that same number back again. So now I know this number is stored in my memory. So if we go on to the second fraction, 188 squared divided by sample size of 60. And we'll take, oh yeah, right. So that's this fraction. I want to add that to the first one. And so I add that to the memory. And so by pressing M plus, I'm adding this number to the memory, and now in the memory I have the sum of both of these numbers. So what is that sum? I just press memory recall, and now I want to take the square root of that. So I'll do that right here, square root. And so there it is. So this number represents the standard error for the difference between these sample means. Now, what am I going to do with that? And eventually, I'm going to take the difference between the sample means, and I'm going to divide by this number. And so I want to put this number now in the memory. To do so, first I need to clear the memory. So I press MC. That clears the memory. And now I'm going to add this number to the memory. And so watch what happens. If I erase and press memory recall, I get that same number back again. So that number is the number that goes on the bottom of this fraction. So to complete the calculation, I take the sample mean from June, subtract from that the sample mean from July, and then I'll divide by this standard error for the difference between those sample means. And that's in the memory. So I divide by memory recall equals, and see I get 6.29259, so that rounds to 6.2926, which is the number you can see here. Right. So, having gone through all that, we now have our test statistic, and now we can draw our conclusion. So we go back to our decision rule. We can see that our test statistic is much bigger than the rightmost critical value. And so that gives us good reason now to reject the null hypothesis. We can reject the null hypothesis at the 1% level of significance because our test statistic is bigger than the rightmost critical value for our test. So lastly, I want to estimate the p-value of the test and then describe, using an adjective, the strength of the evidence against the null hypothesis. And so we'll do that in two ways. First, we're going to use the t-table. And then I'm going to go through Minitab. I'm going to show you how to use Minitab to do this same calculation. And so looking at the t-table, we're looking at a two-tail probability. We're looking at 100 degrees of freedom. And we see here, this of course is the rightmost test statistic, or sorry, take that back, the rightmost critical value for our test. This was the critical value that puts 1% in the two tails combined. And so the point is, if our test statistic was equal to this critical value, and we were to put that number here and here, then the area in those two tails combined would be exactly 1%. However, our test statistic is much further to the right. And so that means the area in this upper tail is much smaller than what it would be if we put 2.626 here. So in other words, hopefully it should be clear that the p-value for our very large test statistic is going to be much smaller than 1%. Now, unfortunately, using a table like this, That's all we can say, that our p-value is much, much less than 1%. Using now Minitab, we'll see we get something else. We can be a little bit more precise about that. So let me now go into Minitab and show you how you could do this same test very easily without troubling yourself with calculations using software. So I'm going to go up here. Hopefully you can see this. I know the font is a bit small, but here I'm going to pick stat. So that means I'm going to calculate a statistic, a test statistic. I'm going to pick basic statistics, and I'm going to go down here. You can see, look, 2 sample t. That's a 2 sample t-test. And so this window comes up, and here we have various options. I'm going to choose summarized data because that's what I have. I have the summarized data, which means the mean values and the standard deviations for the 2 samples. So here now we have a dialog box where I can now put in the sample sizes. Both samples were size 60. The sample mean in the first place was 5224. In the second place it was 5017. The standard deviations were 172 and 188. Let's see. So I'm going to double check that just to make sure that I got that right. So it's 5,224 versus 5,017, 172 and 188. Yep, that looks fine. Okay. So once we have this in place, I'm going to choose some options. The confidence level is going to be 99. And as you will see, part of what Minitab does, it not only conducts the hypothesis test, it also gives you a confidence interval for the difference between the population mean values. And since it's a 1% test, I'm going to look at a 99% confidence interval. The alternative hypothesis is a two-tail test. You can see here you can choose a lower tail, upper tail, or two-tail test. So I got a two-tail test here, and the hypothesized difference is 0. So right under the null hypothesis, the two populations have the same mean value. So I just press OK, and OK, and here we get all of our output. Tells us everything we need to know about our data. So that's how you can set that up in Minitab. And so if we go back to the slides, so just zip through this again, zip through that again. Right, so using the table, all we could say was that the p-value must be smaller than 1%. I mean, after all, that's why we rejected the null hypothesis, because the p-value was less than the level of significance of the test. Using Minitab, so you can see here, this is, again, that's the Minitab output. You can see our 2 samples. We have the sample size, the sample mean, and standard deviation. Here we have the standard error for this sample mean. That's not something we use in our calculation directly, so we don't need to worry about that. Over here, we can see a 99% confidence interval for the difference between those two population means. Notice that this interval doesn't contain 0. And so that's consistent with the fact that we rejected the null hypothesis. Right? And we're concluding that there really is a difference between those population means. In fact, that difference looks like it's fairly large. It could be anywhere between about 121 hours or even as much as 293 hours difference. So a fairly big difference in the mean lifetime for the population of light bulbs manufactured in June versus July. Down here we see we have our test statistic, the degrees of freedom is indicated, and we have our p-value. So we can compare these with what we calculated. So we determined that the test statistic was 6.2926. Okay, so that's in agreement with Minitab. Our p-value, all we could say is that it was less than 1%. And you can see that Minitab is showing it is actually much less than 1%. It's essentially 0. And so what does this mean? This means that we have very strong to overwhelming evidence against the null hypothesis in this instance. Now, just to finish, I want to emphasize how this kind of statistical test has practical value. So imagine if you were in charge of this factory manufacturing light bulbs, and you see that in June, there was a certain mean lifetime of your light bulbs. In July, the mean was significantly less. So there was a significant decrease in the mean lifetime for that batch of light bulbs manufactured in July. So what does that tell you? That tells you that either the materials that you're using were of a lower quality in July compared to June, or it might mean that something went wrong with the manufacturing process, or it could be maybe there was a change in personnel, and so you have, say, less skilled personnel operating on the assembly line. So the point is, once you detect that there was a significant decrease in the mean lifetime of those light bulbs, then it's time to figure out what is causing that. And if you can figure that out, then you can make improvements. And then when August comes, you will take another sample, you will compare August with July, and hopefully you'll see an evidence of an increase in the mean lifetime of those light bulbs. So I'm just trying to say that these statistical tests, even though they're quite theoretical and there's lots of little nitty-gritty calculations, let's remember that there's a practical reason to do these sorts of things. So whatever field that you're going to be entering, it could be a business or marketing, or it could be psychology or nutrition or whatever. It could be the case that at some point you're confronted with data where this kind of test could tell you something important about something to do with your work. So anyways, so that's me on my little soapbox trying to convince you of the value of statistical ideas. In any case, thanks for listening. If you have any questions, you can just write them into the comments. I can check and I can provide you an answer, or you can wait till class and you can ask me then. And that's all for now. So I will say goodbye. Bye-bye.